Hello students, in this module, which is part 8 of our series on differential equations, I'm going to provide an introductory overview of the use of the so-called Green's functions to solve ordinary differential equations. Okay, in the previous module, we saw how we try to understand the solution of this equation, partial squared u, partial like an unsteady diffusion equation, subject to in an unbounded domain, subject to u of x at t equal to 0 as delta x. Then if this is the boundary conditions are u of x tends to plus or minus infinity tends to 0, the solution to this delta function input is the Green's function. Because any arbitrary initial forcing, okay, which we in that example we called k of x minus z t, any arbitrary initial forcing instead of a delta function forcing, f of x can be written as u of x t is integral k of x minus z t f of z dz minus infinity to infinity. So this is the so-called Green's function of this problem. But in this particular lecture, we are going to make a more formal discussion of Green's function. So before I do that, so we'll not do PDEs, we'll do ordinary differential equations. Before that, I'm going to very briefly review the basic properties of Dirac delta function. Okay, so the Dirac delta function is denoted by the symbol delta of t, and it is defined via an integral. So it is not a regular function, it is only defined through an integral. Suppose I have f of x and delta of x minus a dx. Okay, now this turns out to be f of a. Now what is the meaning of this? Okay, let's understand this meaning of this through a simple example. Suppose I have a function like this. Let's say this is my f of x. Now I also have the Dirac delta function, which you know is very sharply peaked, right? It's very sharply peaked or at some point. So this is just figuratively or very cartoonishly depicted here, because it's a very sharply peaked function. This is this is f of x and or delta of x minus a. This is the x-axis. This is the point x is equal to a, where the delta function delta of x minus a peaks. Everywhere else the delta function is 0. So imagine what's happening, and the thickness of this delta function, the width of the delta function is 0. Okay, imagine what you're doing in this integral. You're multiplying f of x by delta of x minus a. Whenever x is not equal to a, delta function is 0. Okay, so when this domain should include, let's say, minus infinity to infinity. If this domain does not include, suppose integration domain does not include the delta function peak, then let's say some a to b, let's use some other symbol instead of a to b. Then let's say y1 to y2 of f of x delta of x minus a dx will be 0 if a does not belong to the range y1 y2, because you are just multiplying f of x by 0 because there is no peak there. So the delta function will contribute a non-zero or will result in a non-zero value of this integral only when the peak is within the domain of integration. Within the domain of integration, when the peak is there, right, now all you have is f of x is very close to f of a, because you can Taylor expand the function f of x about x equal to a. So you will get f of a, which is a constant which can be pulled out, and all you are left with is delta x minus a dx. Now this integral is actually, by definition, its unity. Dirac delta function is like a pulse of zero width and infinite height, such that the area, which is width time height, is 1. So this is actually this is actually 1. So you are essentially left with integral minus infinity to infinity f of x delta of x minus a dx is simply f of a, because this entire thing is unity. Okay, so you can simply remove this. Okay, so you can box this as well. This is an important result. Okay, this is actually unity. So this is an important property of delta function. Okay, so the next thing that you need to know about delta function, it's even. Delta of t is delta of minus t. These are the two things that you need to know. Now let's go to the notion of a Green's function. For Green's function is of course relevant for linear problems. So here we are going to consider linear ordinary differential equations of the form an dny by dx to the power n plus an minus 1, the n minus 1 derivative y, plus so on up to dy dx plus a naught times y of x. Now this is a linear differential equation with coefficients that are in general functions of x, and the right side has a forcing function. The inhomogeneous term is sometimes referred to as a forcing function. Okay, now let's call this operator L. So we concisely represent this as Ly of x is f of x. Okay, this is the differential equation we would like to solve. Now, so with some suitable boundary conditions, so that the problem is well specified. Okay, now so we are interested in solving Ly of x is f of x. Okay, now let's say we have a function g of xz called the Green's function. Okay, such that the solution to this problem y of x can be written as integral over the domain over which you are solving the problem is given as g of xz times f of z, where z is a dummy variable. This is the same function f of x, but here z is the dummy variable of integration. You would like to write the solution to this equation, like to express the solution of that differential equation in this fashion. Okay, then what is g of xz? How do we find g of xz? Now let's operate both sides of this equation by the linear operator L. So Ly of x is L integral a to b g of xz f of z dz. Remember, L has differentials with respect to d dx. Okay, right. So this is given by integral a to b. Because integral is like a sum and L is a linear operator, so L can go in. Okay, L can go inside the integral to give L g of x z, okay, times f of z dz. But from the definition of the governing differential equation, L y of x is nothing but f of x, because that's what we set out to solve in the beginning, right? L y of x is f of x. Alright, so you have therefore f of x being written as a to b something times f of z dz. Now we just saw that this happens only in the case when you have a delta function, because only a delta function, if f of x multiplied by delta x minus a dx, you get f of a. So very similarly, we have on the left side you have f of x, on the right side you have an integral over something which is this times f of z dz. So this must actually be therefore delta of x minus z. Okay, so the Green's function is therefore obtained by solving the Green's function is obtained by solving L g of Green's function is a function of two variables. Remember, delta of x minus z, right? And you have to supply the same boundary conditions at the domain ends x equal to a and x equal to b. Okay, so the Green's function to a differential equation is the solution to that same differential operator, but instead of f of x on the right side, you have a Dirac impulse forcing. This Dirac delta function is also called an impulse function. So this is called an impulse forcing. Okay. So we have to solve if in the original problem y of x equal to a is 0 and these are the BCs, then for the Green's functions you will say g of x equal to a z is 0, g of x equal to b z is 0. Note that Green's function is a function of two variables. You have to use only the x variable for imposing the boundary conditions. Now, because it's a function of two variables, we need additional conditions at x equal to z. Okay, we will derive that in a minute. Before that, I want you to appreciate the following fact, that suppose I have a delta function. Let's say we have a delta function. Peaked at 0. This is the function delta of x as a function of x, because this is peaked at delta of x is peaked at x equal to 0. This is the origin. Now if I were to integrate delta of x, okay, dx, we know that you will get 1. Okay, right, over the entire boundary. So if I were to represent this integral as a function, if I were to integrate this only up to this point, let me use a line. If I were to integrate this only up to this point, you will get 0, because the delta function 0 is 0. Up to x equal to 0, the delta function, if you integrate the delta function, you will not get any contribution, because the delta function is 0. At x equal to 0, it picks up to value 1. So from now on, if you integrate, okay, this becomes constant. It gives you a value of 1. Okay, so the integral of a delta function is actually a Heaviside step function. Okay, so or in other words, if I differentiate a Heaviside step function, if I differentiate a function like this, okay, and then ask the question, what is the solution to this, what is the derivative of this with respect to x, again here you will have 0 everywhere. At this point there will be a spike, again it will go to 0 because again it will go to 0 because out here there is no variation in the function. Okay, so the integral of the delta function is the Heaviside step function, and the differential of the Heaviside step function is conversely the Dirac delta function. Okay, so with this understanding, what we'll next do is to derive the conditions at these are so called the continuity conditions for g of x z at x is equal to z. Okay, now we have L of g of x z is delta of x minus z. Now let's integrate this entire equation over a tiny interval about x equal to z. Okay, so the linear operator is nothing but summation m is equal to 0 to n a m of x, concisely representing the linear operator that, so this is Lg is simply this. Okay, so I'm going to integrate, I'm going to interchange the summation and the integral m is equal to 0 to n, and the integral is done between z minus c and z plus c. That is, the delta function is peaking at x equal to z, so I'm just going to integrate z minus c and z plus c little away and from both sides, on both sides of x equal to z. Okay, so this becomes simply am of x, because this is the operator. L times g is simply, this operator, entire summation, am of x dm g of x z by dx to the m is equal to limit sent to 0 z minus e z plus e. Now because you are integrating the delta function on from either side of the pulse where it is peaking, this integral is unity. Okay, so here we are integrating all these derivatives. Okay, now the highest, so note that integral d to the m g by dx to the m dx, obviously d I'm going to integrate with respect to dx on both sides, I'm sorry. Okay, right, this is nothing but, if I integrate once, I'll get one integral will reduce the power of derivative by 1 by dx to the power m minus 1. Okay, now if you note this, then what you will get therefore is, after integrating, limit epsilon tends to 0 summation okay, so we will have summation, right, m is equal to 0 to n minus 1, or rather 0 to m minus 1. Okay, let me just explain this in words instead of writing it as an expression, right? So what we have is that the highest derivative in the differential equation is dn g by dx to the n, and that is a delta function, right? The highest, see, the delta function is if I integrate at a delta function, I get 1. So the highest derivative, right, because it exists at x equal to z, it has a value of infinity. Therefore all the n minus 1th derivatives must, the highest derivative is infinity, the next highest derivative, right, which is what we want, dn minus 1 by dx to the n minus 1, will suffer, because upon integration dn will become dn to the minus 1 by dx to the n, as we have just seen here. That will suffer a step discontinuity, right? Because that's what we saw. If I integrate the delta function, I'll get a step discontinuity. But if I integrate the step function further, okay, this is a step function, all the higher functions will become continuous, although they have discontinuous slopes, but the function itself will be continuous. So what we can say therefore is that all the derivatives, okay, limit, okay, let me just limit epsilon tends to 0, an of x, the highest derivative when integrated will give me this n minus 1 g of x z. Now that will become 1, but all the other derivatives, a n minus 1 dn minus 2 by dx n minus 2 g of x z will be integrated between z minus epsilon and z plus epsilon, will become 0. Note that if I integrate this, okay, there's one more point that I have to explain. If I integrate this expression, because you are integrating over such a small width, right, this function can be pulled out of the integrand, and all you will have is just dx, which is simply basically you can think of this like a constant, right? So this is a constant. So you are merely trying to evaluate if for all the lower functions. For the highest function you will have to use this. For all the lower functions, okay, the integral of this function is simply z minus epsilon to z plus epsilon, which is 0. That means that these higher derivatives are continuous, okay, that is dn minus 2 by dx n minus 2 of g at z is equal to plus epsilon is the same as dn minus 2 g by dx n minus 2 at z is equal to minus epsilon, and so on. So all these derivatives other than d to the n minus 1 dx to the n minus 1 will be continuous, and the only thing derivative that will suffer discontinuity, if n is the order of the differential equation, then the n minus 1th derivative times the coefficient will suffer a discontinuity. But the coefficient itself is continuous, so that can be pulled out of so this will be simply an of z, okay, out here. This is simply, you are evaluating it at an of z plus e, but an of z plus epsilon and an of z minus epsilon are same to first order, so all you will get is therefore dn minus 1 g by dx n minus 1, okay, at z plus epsilon minus dn minus 1 g by dx n minus 1 at z minus epsilon is equal to 1. So we will come up with this continuity condition or jump condition for the n minus 1th derivative upon integration. Is equal to 1 by an of z, and all the other lower derivatives including dn minus 2g n minus 2 n minus 2g by dx n minus 2 will be 0. Okay, I'll explain this again with the help of a concrete example. So to summarize, therefore, g of xz is a Green's function to an operator L such that L g of xz satisfies delta of x minus z in the right side instead of the original forcing function f. Okay, and g will obey the boundary conditions like the original variable lu is equal to f. Whatever u satisfies, g will also satisfies, whatever that is. Okay, I'm not writing whatever the boundary conditions that are prescribed, g will satisfy the same boundary condition. Now at x equal to z, you have so-called jump or continuity conditions that is obtained by integrating the differential equation, this differential equation, about z minus epsilon to z plus epsilon, and noting that only the highest derivative upon integration will suffer a step discontinuity or a jump discontinuity, but all the other lower derivatives will be continuous. Okay, so let me show this with the help of a very simple second order example in case Suppose I have just this operator, d squared g by dx squared plus g is equal to delta of x minus z. Now all I have to do, first we need to find the jump and continuity conditions. Okay, limit epsilon tends to 0, integral z minus epsilon to z plus epsilon. I integrate this entire equation between z minus epsilon to z plus epsilon, d squared g by dx squared dx plus limit epsilon tends to 0. This equation has no first derivative, so you have second derivative on the function itself, z plus epsilon, okay, g, okay, dx is equal to integral delta of x minus z dx, okay, where x ranges from z minus epsilon to z plus epsilon. Note that the function is peaked at x equal to z. So this quantity is 1. Now this quantity upon one derivative, one integration will give you the first derivative, okay, d dx evaluated at z minus epsilon, z plus epsilon, plus here you have the function itself, right? So, and this is simply g operated at z plus epsilon minus g operated at z minus epsilon, okay, that is equal to 1. Sorry about this. I have to do this slightly differently because this expression, okay, let me first redo this aspect. Okay, so now here you have integral g of xz dz, dx between z minus e and z plus e. This is not a differential, so because this is so the region of integration is so small, this function is virtually a constant, so that will be evaluated at simply g of xz, and then you are taking limit epsilon tends to 0, right? This is also limit epsilon tends to 0, g of xz times z plus e minus z minus e, or epsilon. So this will give me simply limit epsilon tends to 0, g of xz times the z's will cancel times 2 epsilon, but limit epsilon tends to 0 of epsilon is 0, so this will become 0. Okay, I'm sorry about this. So I wrote this wrongly. If you have a derivative dg dx, then that can be integrated, but right now you don't have a derivative, so the function will just integrate like this. Okay, so you have limit epsilon tends to 0, dg by dx at z plus epsilon minus dg by dx at z minus epsilon is equal to 1 in this particular problem, because the coefficient multiplying the second order derivative is 1, so there is nothing. In the previous general case, I had a coefficient 1 over an, so it came as 1 over an here, but here there is nothing like that. Okay, so the derivative of the Green's function suffers a discontinuity. That means the Green's function itself at z plus epsilon and z minus epsilon must be continuous. Okay, if the derivative of a function suffers a step discontinuity, if I integrate this, then I'll have the function will be continuous, but the slope, which is the derivative, will be discontinuous. Okay, so you have two continuity conditions at the location of the Green's function, at the location of the singularity. Okay, now let's now use this to actually solve for the Green function of a problem, and then see, we will work out an example. Okay, so you have d squared y by dx squared plus y is equal to cosecant x. This is our what we called as f of x. In this case, f of x is cosecant x. The boundary conditions given to us are y of 0 is y of pi by 2 is 0, homogeneous boundary condition. So first we have to solve for the Green's function for this problem. How do you do that? You will take g of xz d squared dx squared plus g of xz is equal to delta of x minus z. Okay, instead of the function f, you have a delta function forcing. Okay. Now, how do we solve this Green's function? Except at x equal to z, delta function is 0. So for x greater than z and x less than z, you simply have to solve the homogeneous problem. Sorry. Right? Because x greater than z, the right side is 0, except at the singularity where we will at the location of singularity where we will apply the jump condition. Here also the delta function is 0, here also the delta function is 0. So we write the solution. This is very easily solved, but note that there are two variables. So when I integrate this with respect to z, the constants in general will be functions of when I integrate this equation, I am solving it or integrating it as a function of x. So the constant in general will be functions of z. I have to allow them in general to be functions of z. Sin x plus bz cos x. Let's say this is for x less than z. Okay, and this is cz sin x plus dz cos x for x greater than z. Now the boundary conditions are g of x equal to 0, z is 0, g of x equal to pi by 2, z is 0. This means the first equation will tell you that when I put x equal to 0, cos x becomes 1, sin x becomes 0. So this implies that b of z must be 0. In the second equation, when I put x equal to pi by 2, I will get c of z times 1 plus d of z times 0. That means c of z must be 0. Okay, so therefore the Green's function can be written as az sin x and dz cos x, x less than z, x greater than z. Okay, and we have the conditions jump plus continuity conditions at x equal to z, which will determine the two functions a of z and b of z. So we have g of x z minus epsilon is g of x z plus epsilon, and dg by dx at z plus epsilon minus dg by dx at z minus epsilon is 1. This is the jump condition we derived just before, right? Alright, so now we use these two conditions in this two equations, right? Two representations. So d of z times cos z minus a of z, the first equation, times sin z, because g of x z minus epsilon on both sides is continuous, so they must be equal. So when I subtract them, they will be 0. But the derivative suffers a jump, so what I will do is I will take the derivative minus d of z sin z minus a of z cos z is equal to 1. So I solve for a of z and d of z from these two equations. I'll get, these are two linear equations for a of z and d of z. I'll get a of z is minus cos z, and d of z is minus sin z. Okay, therefore the Green's function g of x z will take the following form: minus cos z sin x, x less than z, minus sin z cos x, x greater than z. Okay, sorry about this. So this is the Green's function. So the solution to Ly is equal to f will be written as y of x is equal to, the domain is 0 to pi by 2, g of x z. Instead of f of x is cosecant x, but here you are using a dummy variable, so you write cosecant z dz. But what is g of z? It depends on what the domain is. When x is greater than z, okay, here z goes between 0 and pi by 2, and so you write this as 0 to x plus x to pi by 2. So here z lies between 0 and x, whereas in the second integral z is greater than x. In the first integral, z is less than x. So when z is less than x, we know what the form for the Green's function is. That is when z is less than x. So you have to use this. Okay, x is greater than z. Minus sine z cos x. Okay, minus sine z cos x cosecant z dz. Here you will have x less than z. Okay, minus cos z sin x z sin x cosecant z. Okay, so if I integrate this, so I can pull out this cos x, because the integral is only as a function of is with respect to z. So minus sin z cosecant z dz. Similarly, minus sin x cos z cosecant z dz. Okay, so this, for this particular case, if you do the integral, you will get minus x cos x plus sin x ln of sin x. Okay, this is the solution to y of x to the original problem. Ly is equal to cosecant of x. Okay, using the Green's function method. You first solve for the Green's function, right? And then you substitute the Green's function, and then you substitute the general solution is this f of z. In this particular case, f of z is cosecant of z. Okay, but the power of the Green's function method is that once you have found the Green's function, you can solve it for any function, any functional form f of x. Okay, so it need not be for just the given function. You can, if somebody gives you another function, you simply have to do the integral once again, because you have already found the Green's function once. Now, one important detail that I would like to tell is Green's functions are sensitive to boundary conditions. That is, the Green's function is defined, even though the operator is the same, it depends on the boundary condition. So d squared y by dx squared plus y, the same operator. Let's say now both the conditions are at x equal to 0, y of 0 0, dy by dx is also 0. Now in the same way we will proceed. G of x z is a of z sin x plus b of z cos x, c of z sin x plus d of z cos x. This is x less than z, this is x greater than z. Okay, so and then we have the condition g of 0 z is 0, dg by dx of 0 z is 0. Okay, if I do this, I'll get a of z is 0, b of z is 0. Okay, both these constants will become 0. Okay, therefore, and then you have the continuity conditions, continuity jump conditions at x equal to z, which will say that c of z sin z plus d of z cos z is 0, and c of z cos z minus d of z sin z is 1. This is the derivative condition, this is the function condition. Okay, so if you solve, you will get c of z is cos z and d of z is minus sin z. Okay, then therefore we will get the Green's function as g of x z is 0 for x less than z, and if I simplify the trigonometric expression, I'll get sin x minus z for x greater than z. So again, the solution to the differential equation is y of x is, there is no upper bound in the domain, so we can take it as infinity, g of x z f of z dz. Okay, and g of x z is sin x minus z. Okay, and 0 to x. Okay, I'm sorry, this is 0 to x. Okay, and the lower bound is 0. Okay, in the previous case you had 0 to pi by 2, but here okay, so let me step back a little bit. There is no upper bound, so you take this as 0 to infinity, so you will write this as 0 to x. Let me do it properly, plus x to infinity. Let me not write down the functional form now. Let me just write g of xz f of z, and here also I'll write g of xz f of z dz. Now note that when x is greater than z, when x is greater than z, here x is greater than z because z lies between 0 and x. Here g of xz is sine of x minus z. When x is less than z, g of x is 0, so this is 0. So finally what you will get therefore is y of x is integral 0 to x sine of x minus z f of z dz. Okay, so here the idea is to show you or demonstrate you the fact that the Green's function is also the nature of the Green's function is also a function of boundary condition. Okay, now one last illustration regarding Green's function, and that relates to Green's function as a superposition of eigenfunctions Okay, so let's imagine that. So let's say you have a linear operator. You are interested in solving Ly of x is equal to f of x. Okay, now let's say there is a corresponding eigenvalue problem, okay, for L such that L phi n is equal to lambda n rho of x phi n of x, where these are the, let's say L is a self-adjoint operator. Sorry about this. Self-adjoint operator, and therefore the eigenfunctions are orthonormal. Okay, and these are the eigenvalues, of course, and rho is the weighting function that in the Sturm-Liouville problem. So once I solve for the eigenvalue problem and for the differential operator L, I can hope to write the solution for this problem as y as some Cn phi n of x. Okay, now I'm going to operate this equation on both sides with Ly. Ly is nothing but f from the governing differential equation here. Okay, so Ly is f, but on the right side I have L operating on Cn phi n. Because L is a linear operator, I can pull this in Cn L phi n, but L phi n is nothing but from the eigenvalue problem Cn lambda n rho n of x times phi n of x. Okay, so this is f of x. So what are Cn's? You have to take inner product with respect to yj, let's say. So integral a to b phi j star of x rho of x. Okay, let me say phi j star of z. Okay, phi j star of z rho of z times f of z. Let's say that I'm writing for a particular reason, I'm writing everything as a function of z now. Okay, the reason for this will become obvious soon. Okay, for fence, because these are just dummy variables, whether it's x or z, right? F of z dz is summation. Of course, there is a counter n going from 0 to infinity in principle in these sums. If I miss writing it, please note it. Okay, so a to b. Okay, I'm this is nothing but Cn lambda n phi j star of x phi n of x Okay, rho of z rho of z times dz. Okay, all right. So okay, let me back up a couple of steps to be clear. Sorry about this. Okay, so what we did was we found that you had f of x, which is L y of x, and instead of y of x I'm writing L phi n of x, and because L is a linear operator, I take it this side. Since n is 0 to infinity, Cn. Now L phi n is lambda n rho n of x phi n of x, right? And this is f of x. To find the constant Cn, you have to multiply both sides by phi j star of x and integrate between the domain, let's say a and b. Okay, so in the previous step, which I erased now, I had inadvertently multiplied by rho n on the left side. That is not necessary. Okay, so what all you have to do is say that a to b phi j star of x, okay, and right, phi j star of x f of x dx is nothing but summation n is equal to 0 to infinity, right, Cn integral a to b. Now lambda n also comes out. Rho of x is already there. Phi j star of x phi m of or phi n of x, I'm sorry, dx. Okay, now what is this? This is delta of, this is n, I'm sorry, delta of jn, because phi j phi n are orthogonal with respect to this weighting function. Okay, now therefore delta of jn, okay, summation delta of jn c n lambda n, the delta jn will kill the sum to give cj lambda j is a to b phi j star of x f of x dx. Okay, so this is the way you find the constants. So the constants are nothing but 1 by lambda. Suppose instead of j, if I say n, Cn is 1 by lambda n a to b phi n star of x f of x dx. Okay, now y of x, the function on the right side, is summation Cn yn of x, sorry, phi n of x, sorry, the y of x is the solution that we are after, right? We are expanding y of x as in the eigenfunction expansion. So y of x is summation n Cn phi n of x, but we know what is now Cn in terms of the eigenvalue problem. We just found Cn's to be this, so I can substitute Cn's out here to get y of x is nothing but summation n is equal to 0 to infinity 1 over lambda n integral 0 a to b, sorry, phi n star of z. Now because here there is x and these constants are integrated over some dummy variable x here, this x is not the same x here, so I'm using the dummy variable z. So here I could have equally written z z z. Okay, so in the same way I'm writing phi n star of z by phi of z dz. Okay, So I'm assuming the eigenfunctions to be orthonormal, so this becomes delta Jn. Okay, so you have this, right? Y of x is, instead of Cn, I'm writing, okay, let me pull this a little bit closer, and you will note that this entire block is Cn, okay, times I have to write phi n of x. Okay, I'm sorry, this is f of z dz. Okay, so I can rewrite this as, I can integrate the integrals and sum integral a to b summation n is equal to 0 to infinity, right, 1 by lambda n phi n star of z. I'm going to pull this phi n here inside phi n of x, and then I'm going to pull out f of z dz. So y of x is this times f of z dz. Okay, but from the definition of Green's function, we know that if I have a problem Lu is equal to f and y is written as integral of g of x minus z f of z dz, right? So this whole thing is actually, this entire thing is actually the Green's function to the problem g of x z. So by appealing to the notion here, this should be y of x. Okay, so that means that you have found an alternative way of expressing the Green's function to a linear operator in terms of the eigenfunctions of the operator. N is equal to 0 to infinity 1 by lambda n, where lambda n is eigenvalue, phi n star of z phi n of x. So there are two variables. So this is another way of expressing the Green's function to the problem based on eigenfunction expansion. Okay, if the operator is not simple enough to solve for, like the one we illustrated at the beginning of this module, if you still want to obtain the Green's function to a linear operator, there is this alternative way of doing it. Okay, I'll stop here. So with this, we have given a rough overview of various solution techniques for solving linear, ordinary and partial differential equations. Of course, many problems in reality, in chemical engineering and other engineering and physical sciences will involve nonlinear equations as well, and for that you need numerical methods, but they all have their basis in many of the fundamentals that we have covered, such as eigenfunction expansion, matrices, linear algebra and so on. So all these are an absolute prerequisite for solving nonlinear problems. Okay, with this I'll stop here.